Today I want to ask a simple question. Is there a limit to how bright the universe can get? The cosmos is full of obscene extremes, stars that die in catastrophic supernovae, quasars that outshine entire galaxies, and black holes spiralling together sending ripples through spacetime itself. These events are so violent that for brief moments their power output can exceed billions of stars combined, which raises a simple but unsettling question. How bright is too bright? To answer this question, we need a single yardstick, one number that lets us compare the most extreme events the universe can produce. That number is luminosity. Luminosity is defined as the rate at which energy is emitted by an object, and we can write it as L equals delta E divided by delta T, where delta E is the energy emitted over a time interval delta T. Since energy is measured in joules and time in seconds, luminosity has units of joules per second, more commonly called watts, and 1 watt simply means 1 joule of energy emitted every second. For reference, a typical household lamp runs at about 10 watts. That means it releases roughly 10 joules of energy every second into the room. On the other hand, the peak radiative luminosity of a megaton class nuclear explosion can briefly reach around 10 to the 15 watts, making it one of the most luminous human-made events. By comparison, the sun shines continuously at about 10 to the 26 watts, not for seconds, but for billions of years, and yet even the sun is small fry compared to some of the cosmic monsters roaming our universe. When a massive star dies in a supernova explosion, its peak luminosity can briefly reach around 10 to the power 36 watts, comparable to the combined starlight of a small galaxy. Quasars can reach 10 to the power 40 watts, outshining hundreds of billions of stars. But the most extreme luminosities we've ever observed don't come from light at all. They come from gravity. When two ultra-dense objects like neutron stars spiral together and collide, they send ripples through the fabric of spacetime itself, gravitational waves racing outwards at the speed of light. And when the colliding objects are black holes, the effect is even more extreme. In the final fraction of a second before they merge, the energy carried away as gravitational waves can momentarily reach around 10 to the power 49 watts, the most intense burst of power ever observed in the universe. At this point, the question becomes unavoidable. Is there any limit at all to how luminous an object can be? Or is there a fundamental ceiling, a maximum possible luminosity, written into the structure of the universe itself? That is what we're going to explore today. So sit back and enjoy the ride. Now, the first thing you might reasonably ask is, why should there be a limit at all? Why couldn't an arbitrarily large amount of energy be released in an arbitrarily short amount of time? That question cuts straight to the heart of why relativity matters here. According to Einstein's special theory of relativity, nothing can travel faster than the speed of light. And according to Einstein's general theory of relativity, if you pack too much energy into too small a region of space, gravity takes over and that region collapses and a black hole forms. Okay, so what does any of this have to do with luminosity? Imagine you have some region of space of size r, and you want it to emit as much energy as possible as quickly as possible. If you think about it, the fastest conceivable way that energy could escape this region is at the speed of light, because special relativity forbids any transfer of energy or information from happening faster than this. So the most extreme case you can imagine is that the energy leaves in the form of something that itself travels at the speed of light, like electromagnetic radiation or gravitational waves. In that case, the shortest possible time it can take to escape the region is simply the light crossing time equal to r divided by c. Okay, so far so good. But to maximise the luminosity, we don't just want energy to escape quickly, we also want to pack as much energy as possible into this region to begin with. After all, the more energy it contains, the more it could in principle release per second. But this is where gravity now rears its head. Einstein's general theory of relativity tells us that space-time isn't a rigid stage. It bends and curves in response to energy and mass, and if you try to concentrate too much energy into a fixed region of space, general relativity predicts that the region will collapse behind an event horizon and form a black hole. And that's a problem, because once a black hole forms, nothing can escape. So the question becomes, how much energy can you squeeze into a region of size r before it collapses? Well, according to Einstein's theory, if we take a spherical object of mass m and gradually reduce its radius while keeping its mass fixed, there comes a point where the density becomes so large that nothing can prevent gravitational collapse and a black hole forms. The critical radius where this happens is called the Schwarzschild radius, and it can be calculated using a remarkably simple equation, that r is roughly equal to gm over c squared, where m is the mass of the object, g is the gravitational constant, and c is the speed of light, and where we've deliberately dropped numerical factors since we're only interested in an order of magnitude estimate. The Schwarzschild radius marks the event horizon, the boundary beyond which nothing, not even light, can escape. Crossing this boundary means crossing the ultimate point of no return. And this tells us something crucial. If our region has size r, then the largest mass we can fit inside it without forming a black hole is roughly the mass whose Schwarzschild radius is equal to r, such that we can write rs is roughly equal to r. In that case, we can write that r is roughly equal to g times m max divided by c squared, and if we rearrange this, we see that the maximum possible mass we can squeeze into the region is of order rc squared divided by g. Now, we can turn this into a statement about maximum energy rather than maximum mass by using the fact that, according to Einstein's special theory of relativity, energy and mass are related by the famous equation E equals mc squared. And so if we now combine our two equations, we see that the maximum energy is given by rc to the 4 divided by g. This says that the maximum energy grows linearly with the size of the region of space, which is signified by r. At this point, everything comes together. We know the maximum energy the region can contain, and we also know the minimum time in which that energy can escape. And luminosity is just energy divided by time. And so to estimate the maximum possible luminosity, we simply take the maximum energy and divide it by the minimum time. And if we sub in the explicit expressions we've derived and simplify, we end up with a remarkably compact expression, c to the power 5 divided by g. And this is quite an astonishing result. We see that the size of the region, r, has completely disappeared. We're left with a number that depends only on two fundamental constants, the speed of light, which limits how fast energy can move, and Newton's gravitational constant, which tells us how strongly energy itself gravitates. Now, if we plug in the numbers, we get an eye-watering value of roughly 10 to the power of 52 watts. That is 10 million billion 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 joules per second, which is 100 trillion trillion times the luminosity of the sun. And this extreme luminosity actually has a name. It's known as the Planck luminosity. Now, the universe is full of extreme objects and events that generate mind-bending luminosities, things like quasars and gamma-ray bursts and mergers of black holes, and some of them reach powers that are a non-negligible fraction of this bound. But no confirmed observation has ever exceeded it. What's even crazier is that the Planck luminosity exceeds the combined luminosity of every star in every galaxy in the observable universe. If we take a typical solar luminosity of 10 to the power 26 watts, such as that of our Sun, and multiply it by the estimated number of stars in the observable universe, roughly 10 to the power of 23, the resulting luminosity is still less than 1,000th the Planck luminosity. Now, you've probably heard of other Planck quantities before, the Planck length, Planck time, and Planck mass. I've made videos exploring these scales and how they appear in modern physics. One thing that you will immediately notice is that the Planck quantities are built from the fundamental constants that appear in our deepest physical theories. Notably, we have the speed of light, c, which represents the ultimate speed limit in the universe and lies at the heart of Einstein's special theory of relativity. We have Newton's gravitational constant g, which appears in Einstein's general relativity and tells us how strongly mass and energy curve spacetime. And we have Planck's constant h bar, which sits at the foundation of quantum mechanics, governing the physics of the very small. In that sense, these three constants correspond to three great pillars of modern physics: the very fast, the very massive, and the very small. And it's worth noting something. Quantum mechanics and Einstein's special theory of relativity are already unified. That unification is called quantum field theory. In quantum field theory, particles are excitations of underlying fields, and the theory is built so it automatically respects special relativity. That's why C and H bar naturally appear together. The real missing piece, the unsolved problem, is how to bring gravity into the picture. Now, if you look again at the Planck length, Planck mass, and Planck time, you'll find that all three constants, C, G, and H bar, appear together. They're telling us the scale where we expect quantum effects and gravity to become inseparable, the regime where a quantum theory of gravity should reveal itself. Now, notice something interesting. We can actually recover the Planck luminosity in a completely different way, using the Planck mass and Planck time. To do that, we start by forming the Planck energy. That's just the mass energy associated with the Planck mass, which we can write as the Planck mass multiplied by the speed of light squared. Now, once you have an energy, there's a natural way to turn it into a luminosity: divide by time. So if we take the Planck energy and divide it by the Planck time, we get a natural luminosity scale. And then if we plug in the definitions of the Planck mass and Planck energy and simplify, we end up with c to the power 5 divided by g, which is exactly what we had before. And notice what has just happened. Planck's constant has cancelled out completely. The Planck luminosity depends only on c and g, relativity and gravity, with no explicit dependence on h bar at all. Okay, so what is this telling us? Well, it suggests that a maximum luminosity is a purely gravitational and relativistic limit, and whenever a Planck scale quantity can be constructed without h bar, it signals something fundamentally classical. In other words, the Planck luminosity appears to be a classical limit. And this immediately raises a deeper question. Is this just a coincidence, or is there something genuinely special about the kind of spacetime we live in that allows this to happen? To find out, we're going to do something simple but radical. We're going to imagine changing the number of dimensions of spacetime, more specifically the number of spatial dimensions, and ask how gravity, and ultimately luminosity, behave in those hypothetical worlds. One thing I've learned from studying physics is that problem solving is a transferable skill. And right now, one of the fastest growing areas where problem solving really matters is AI automation. Companies like Meta, Nvidia, and IBM are investing billions into AI infrastructure, and the demand for people who can build and automate AI workflows is skyrocketing, even though many people have never even heard of these jobs. The surprising thing is, you don't need a technical degree or any coding background to get started. That's where Careerist's AI Automation Bootcamp comes in. It's a 4-month online program, around 6 to 7 hours a week, that teaches you how to automate real-world workflows using AI tools, build actual projects, and create a portfolio that you can show to employers. Careerist graduates have landed jobs across 42 US states, and the program includes an internship, portfolio creation, and job placement support, so you're not doing this alone. If you're a career changer, a student, someone looking for remote work, or just someone who loves solving problems, it's a great path for anyone who wants to apply their skills in a new field. No degree, no coding, just curiosity and a willingness to learn. If you want to explore this opportunity further, visit crst.co/5kksy or click the link in the description. There are special discounts available, plus a free career consultation and financing options. If you've been considering a move into tech, this is a really accessible way to get started. So let's consider a hypothetical universe with d dimensions of space and 1 dimension of time. Our goal is then simple: to understand how gravity behaves in such a universe and what that implies for luminosity. We're going to start with something familiar. In 3 spatial dimensions, gravity follows the inverse square law, which we can write as F is proportional to 1 over r squared. This is simply telling us that if you double the distance between 2 masses, the gravitational force reduces by a factor of 4. If you treble the distance, the force reduces by a factor of 9. This is what inverse square law means. But you might not realise that this behaviour is actually unique to a three-dimensional world. Imagine placing a mass at the centre of space. We can visualise the gravitational field it produces using field lines that point radially inward towards the mass, with the density of those lines indicating the strength of the field. Now imagine surrounding the mass with an imaginary spherical surface. The total number of gravitational field lines passing through the surface is called the gravitational flux. And here's the key point. That total flux must be the same for any sphere that encloses the mass, no matter how large the sphere is. In three spatial dimensions, the surface area of a sphere grows like r squared. So as you move farther away from the mass, the same total gravitational influence is spread over a surface whose area increases as r squared. To keep the total flux through the sphere constant, the strength of the gravitational field must decrease in exactly the opposite way. In other words, the force must fall off as 1 over r squared. This is the familiar inverse square law of gravity. But here's the crucial point. The way in which the surface area of a sphere depends on radius depends on how many spatial dimensions you live in. In a universe with d spatial dimensions, the surface area of a sphere no longer scales like r squared. Instead, it scales like r raised to the power of d minus 1. And as a result, the gravitational force must fall off as 1 over r raised to the power of d minus 1. And so Newton's law of gravity in a universe with d spatial dimensions can be written as g subscript d times m1 m2 divided by r raised to the power of d minus 1, where g subscript d is the gravitational constant appropriate to d spatial dimensions. In other words, the gravitational constant takes different values in different dimensions, and so our next step is to explore what this means for the concept of maximum luminosity in different numbers of spatial dimensions. Now, up to this point, when I've used the word dimension, I've meant spatial dimensions, the number of independent directions in space, which is what d represents. But from here on, I'm going to also be using dimension in a different sense when I refer to the physical dimensions of a quantity. And to do that, we're going to use a tool called dimensional analysis. Instead of tracking units like meters, seconds, and kilograms, dimensional analysis tracks the underlying physical dimensions that those units represent. For example, mass is a base physical dimension, whereas the kilogram is just one particular unit used to measure it. The other base physical dimensions we'll use are length, often measured in meters, and time, often measured in seconds. Now, when we do dimensional analysis, we're not going to worry about the units. Rather, we will express all quantities in terms of their base dimensions, L, T, and M. Okay, so let's start with something familiar. Force is defined as mass times acceleration, and so the dimensions of force, which we indicate with square brackets, are equal to the dimensions of mass times the dimensions of acceleration. Then the base dimensions of mass is simply m, and the dimension of acceleration will be equal to the base dimensions of velocity divided by time, which we write as L times t to the minus 2. And so we see that if we combine our results, then the base dimensions of force can be written as m times L times t to the power of minus 2. Okay, so now that we have the physical dimensions of force, we can return to the d-dimensional gravitational force law, which, if you recall, took the following form. Our task is to now determine the dimensions of the gravitational constant. To do that, we first rearrange the force law for g, and then taking the physical dimensions of both sides gives the following expression. Okay, so what next? Now, we've already derived an expression for the dimensions of force, and we also know that the dimension of r is length and the dimension of m is mass. And so if we sub these into our dimension equation and simplify, we end up with the following expression for the physical dimensions of the gravitational constant in d-dimensional space. And this is the result that we wanted. We see that the physical dimensions of the gravitational constant change with the number of spatial dimensions. And so we're now finally ready to ask a crucial question. What happens when we try to build a fundamental luminosity scale in an arbitrary number of spatial dimensions. So let's now answer this question. To do that, recall the expressions that we had for the Planck length, Planck mass, and Planck time. And we see that each involve a factor of h bar, c, and g. So let's now suppose a fundamental luminosity scale exists built from these same three constants. Only now we're not going to specify how many spatial dimensions there are, and we're going to leave d as a free parameter. In other words, we're going to write the luminosity as being equal to Planck's constant raised to some power alpha multiplied by the speed of light raised to some power beta multiplied by the d-dimensional gravitational constant raised to some power gamma. And then the task is to see if we can fix alpha, beta and gamma by using dimensional analysis and by requiring that the physical dimensions match on either side. So our next task is to sub in the explicit dimensions for each of the quantities appearing in our dimensional equation. The good news is that this is relatively straightforward. First, the dimensions of luminosity are equal to the dimensions of energy divided by time, which can be written as ml squared t to the minus 3. Next, the dimensions of the speed of light are simply length divided by time, and the dimension of Planck's constant are equal to the dimensions of energy divided by frequency, which is equal to ml squared t to the minus 1. And we've already derived an expression for the dimensions of the gravitational constant. So we now have all the ingredients. If we sub all these expressions into our master equation, we end up with the following monstrosity of an expression. But not all is bad. If we expand out the exponents and gather terms, we can rewrite our dimensional equation in the following form. And the task is now to ensure that the dimensions match on either side. To do that, we require that the exponents of m, l and t match. So, for example, looking at the exponents of m, for these to match, we require that alpha minus gamma is equal to 1. Looking at the exponents of L, we require that 2 alpha plus beta plus d gamma is equal to 2. And finally, looking at the exponents of T, we require that minus alpha minus beta minus 2 gamma is equal to minus 3. So we now have a set of simultaneous equations that can be solved. So if we go ahead and do that, we find the following values for alpha, beta and gamma. And we immediately notice that each of these values explicitly depends on the number of spatial dimensions, d. And if we now sub these values back into the general expression that we had for the d-dimensional Planck luminosity, we find the following rather ugly looking expression. But this is exactly what we wanted. Specifically, if you look at the exponent of h bar, which is what I've called alpha, then you can see that it is only when d equals 3 that alpha equals 0, meaning the Planck luminosity contains no factors of h bar at all. And we see that for any other value of d, other than 3, this exponent is non-zero, which means the luminosity scale depends explicitly on h bar. But if d equals 3, then alpha vanishes, and when that happens, Planck's constant drops out entirely and the luminosity reduces to c raised to the power of 5 divided by g, exactly as we found earlier. So this isn't a coincidence, and it isn't just an artifact of how we define Planck units. Rather, we see that only in a universe with 3 dimensions of space do gravity and relativity conspire to produce a maximum luminosity that's purely classical, independent of quantum mechanics. In any other number of dimensions, the maximum luminosity would be a genuinely quantum gravitational quantity. So the absence of h bar in the Planck luminosity isn't an accident of notation. It's a deep statement about the universe that we actually live in, and about the dimensionality of space itself. Now, at this stage it's worth mentioning that saying there's a classical maximum luminosity is essentially the same as saying there's a classical maximum force, the so-called Planck force. To see this, imagine any process that delivers energy at a rate L equals dE by dt. This is effectively the definition of luminosity. If that energy is carried by something moving at the fastest possible speed, c, like radiation, then energy and momentum are linked by the relation P equals E over c. And so we see that a luminosity implies a momentum flow. And so we can write that dp by dt is equal to 1 over c times dE by dt, where we've just used the relation P equals E over C and the definition of luminosity. And this is simply equal to L divided by C. Finally, we recall that the rate of change of momentum, dP by dt, is what defines a force, F. And so we see that in the case of a maximal speed energy transfer, the force is related to the luminosity by the simple equation F equals L divided by C. It then follows that the maximum force will be related to the maximum luminosity in the same way. And if we sub in the Planck luminosity for the maximum luminosity and simplify, we see that the maximum force is equal to c to the power of 4 divided by g. And this is known as the Planck force. And it's interesting to note that there are physicists, most notably Christoph Schiller, who've argued that you can go even further. That much of Einstein's general theory of relativity can be derived from the assumption that nature admits a universal maximum force, or equivalently, a universal maximum power. Now, even though the Planck luminosity in 3 spatial dimensions does not depend on h-bar, that's not the same as saying quantum mechanics is irrelevant to the processes that might come close to it. So to end the video, I want to focus on something that mixes the classical and the quantum in the most dramatic way possible: the last breath of an evaporating black hole. Now, as you probably know, Hawking radiation predicts that black holes aren't perfectly black. They radiate energy, and crucially, the smaller a black hole gets, the hotter it becomes, and the faster it radiates. In fact, it is well known that the Hawking luminosity scales like h-bar c to the 6 divided by g squared m squared. And for those interested, I have a video outlining a derivation of this result. The key observation is that as m decreases, the luminosity rises like 1 over m squared. But as a back-of-the-envelope estimate, the luminosity ramp-up can only continue until the black hole reaches roughly the Planck mass, because below that we no longer trust the semi-classical approximation underlying Hawking evaporation. A theory of quantum gravity is needed. So let's do the simplest possible estimate. We set the mass equal to the Planck mass, where, if you recall, the Planck mass was the square root of h bar c divided by g, and if we insert this into the Hawking luminosity expression and simplify, we end up with c raised to the power of 5 divided by g. So in this crude but very suggestive back of the envelope picture, the final stage of evaporation naturally approaches the Planck luminosity scale. The catch is that the end point, a Planck mass black hole evaporating in something like a Planck time with something like a Planck luminosity, is highly speculative because the last moment sits squarely in the regime where we don't yet have a complete theory of quantum gravity. And who knows, maybe someone watching this video will help take the next step towards that elusive theory of quantum gravity. And that is where we'll end for today. So thanks for watching, and until next time, goodbye. And as always, a massive thank you to all my patrons, and a special shout out to the following who have been incredibly generous with their support. Thank you so much. I couldn't do it without you.